Number 34. A commuter train blows its 200 hertz horn as it approaches a crossing. The speed of sound is 335 meters per second. Letter A. An observer waiting at the crossing receives a frequency of 208 hertz. What is the speed of the train? So this is Doppler effect, right? Check out number 30 for a detailed discussion on how to think through the formulas and what it all means. We're going to do a shorthand here, okay? So we got two formulas that deal with Doppler effect. We have SMO, S-S-M-O, and SOMS, S-O-M-S. SMO, S-S-M-O, stands for Stationary Source Moving Observer, and SOMS stands for Stationary Observer Moving Source. Now, the way to remember which one goes with which formula over here on the right, remember SOMS has the signs and the bomb-bombs. SOMS and the bomb-bombs, okay? So that's an easy way to try to remember them. I explained where that kind of comes from in number 30. So what we realize here is that we have a commuter train that's moving, right? And we have an observer that's waiting and stationary. So we have a stationary observer and a moving source. So we know we're going to be using that formula, all right? So let's write it out. So frequency of the observer, or frequency that the observer is experiencing, is equal to the frequency that the source is producing multiplied by the velocity of the sound, divided by the velocity of the sound, plus or minus the velocity of the source. Okay, in this question, right, the source is the train, and they're asking us what's the speed of the train, so they're asking us what's the velocity, right, of the source, or aka the velocity of the train. Now, we have to be careful because we got a plus minus in here. We got to think through which one we're talking about. So it says it's approaching a crossing and the observer is at the crossing. So the source, the train, is approaching the observer, right? And we know when it approaches, we're using the minus sign and instead of the plus. Again, number 30, I went through that. So now all I have to do is basically solve this thing. You can plug in the numbers now if you wanted, or I can just solve this algebraically for V sub s. Okay, it doesn't really matter how you work through it on this particular problem. So what we'll do is, why don't we just solve it algebraically first? Okay, and I'm just thinking, yeah. So let's do it this way. So divide out. There's a couple of ways you could think it through. I guess, yeah. So why don't we do this? So frequency of the observer is equal to then Fs times Vw, right? We can just simply multiply those two. They're being multiplied anyway. So that's not a problem here. So we can take Fs times Vw all over Vw minus Vs. Simply do a cross multiplication. I got to get Vs by itself, so I'm going to bring that on over, bring this on down. Great. And now I got to have a positive velocity of the source. So I'm going to add that on over to this side. That means I got to subtract this on over to the left. In other words, right, the velocity of the source will be equal to the velocity of the sound minus then the frequency of the source times the velocity of the sound, all divided by then the frequency of the observer. And we notice that both of these have the velocity of sound in common, so we can pull that out if we wanted. So we can simplify this to be the velocity of the sound multiplied by now 1 minus the frequency of the source divided by the frequency of the observer. And it works out to be a nice little formula here, right? So I might refer you guys back to this problem if I want to just use this in future problems, might save a little time. So now all we have to do is plug in the values, right? So we have the frequency of the source, we have the velocity of the sound here, right? Is going to be 3 velocity of the sound. What do they tell us? Speed of sound is 335 meters per second, so that's 335. Multiplied by now 1 minus the frequency of the source. So it says the source is 200 hertz, right? That is the sound that that's the frequency that the horn is producing, right? So that's 200, divided then by the frequency that the observer is experiencing. And the frequency the observer is experiencing is 208 because it's higher, right? The train's moving toward him or her. And just calculate now. So we get 335 multiplied by now 1 minus 200 divided by 208. And what do we get? We get about 12.9 or so, right? So the frequency of the source, the train, is moving at about 12.9 meters per second. Voila. And now for letter B. What frequency does the observer receive as the train moves away? All right, so basically we got to kind of redo the calculation a little bit, right? We're now going to use the same thing. The train is still moving, so we're still using the same formula, but since it's moving away, we're going to use the plus in here, okay? So for letter B, it's going to be the frequency of the observer, right? And it's saying, what frequency does the observer receive? So this is what we're looking for, all right? Will equal then, and I'm just copying this formula. The only thing I'm going to change is the plus sign in there, is equal to the frequency of the source. So the source, again, is 200 hertz. Multiplied by the frequency, the velocity of the sound, which is 335, divided by the velocity of the sound, which is 335, plus now the velocity of the source. We just found that. That's the 12.9. Okay, probably use the exact value when I calculate it. So the frequency that the observer experiences will be, here we go. So it's going to be 200 multiplied by 335 divided by parenthesis 335 plus then that exact value, close those parentheses. We get a value of about 193, I guess, considering rounding, 193 hertz. And it should be lower than, right, as the train moves away, you know the frequency goes down, you hear a lower pitch. There you go, guys. All right, thanks for tuning in. Appreciate it very much. Please remember to subscribe, and we look forward to helping you with more problems. Take care.